Good morning, everyone.
Good morning, Professor.
So we're back from our exam and sort of a break. Hope you had a chance to relax and unwind after the exams, all of them. And now we're back to class. So this week, or today rather, we'll be doing review from our midterm, which I'll talk about more in a moment, and then some review of exponent rules. Exponents are also not, sorry, I forgot to turn my light on there. Exponents are not like a content area of the class. I'm going to review some of the rules because I know it's a thing that maybe for some of you, you just haven't done it in a while. So good to do a bit of have a bit of a refresher. But it's not like considered an area that I feel is necessary to teach. I expect everyone to have learned all these rules in the past. So we'll do the review today. But if there are parts of that you have kind of completely forgotten, then I've posted review questions and such that you should be working on. But the rules that we'll see today, I'm not going to like formally teach the whole rule. I'm expecting that you've learned it and we just kind of need to be reminded of a few things. So up to this point in the class, we've been dealing with straight lines or various kinds of linear relationships. After the midterm, our area or our focus is all sorts of not straight lines, these kinds of things. What are the equations of these things? How do we find the maximum of that or the minimum of that, or this weird sort of halfway between point here and that kind of thing. So those are the relationships we're going to. So things are going to get a little more complicated than what we've been doing so far in the course. Just a heads up. Right. So let's talk about the midterm a bit briefly here, and then I'll talk about what we will be doing for the second half of the course, and then we'll get on with the midterm review. So midterm grades are, not back to you yet, obviously. We're almost done with the grading, probably by the end of today. I expect sometime this evening, I'll be ready to send all of it back to you. I will report your kind of overall grade for the midterm, not your each individual question score. That's a lot more work to report each of those to you. If you do want to know what was your score on a particular question, you're welcome to come and talk to me in office hours, and I'll break down this question. You got this many points, you had a mistake here, etc. So I'll give you your grade for the midterm and also your rank in the course. As I'm sure you know, there's a limited number of students who can get A's or B's. So I'll tell you there are this many students registered in the course, and of them your rank 15 or 32 or whatever it is. So you'll get both of those things when the grades are ready, probably by the end of today. Right. Final exam. Final exam will include midterm material. 25%. 1/4 of the final exam content will be on pre-midterm material. So all the stuff that you've done and we're studying for the midterm. Also, the other 75%, like if we're going to learn how to graph a line that looks like this, that's the equation of a non-curved line. It builds on the whole ideas from equations of linear relationships of straight lines. So the stuff that we've been learning so far, or been practicing so far, definitely will be needed is background knowledge needed for this kind of thing. But then also on top of that, 25% of the final exam content will be directly testing the pre-midterm material. So it's all still useful, and your future courses will all be using this stuff. So it's all very useful and good to know. Any questions about kind of big picture things about the exam? Anyone wants to ask? Okay. All right. So I posted that survey on Saturday or Sunday, and a lot of you did it. And almost everyone said they want to do at least some amount of review based on the midterm. So that's what we'll get to now. When I do this review, I'm going to be talking about the strategies and how to solve these questions. I'm not going to take the time to like one by one do the full solutions for every single question. I don't think that's a good use of time. You still have all your answers. You know exactly what solutions you gave. So I'll talk about the strategies and generally how to solve these questions, and then you can take a look at whether or not your solutions were like that, were using that same kind of pattern, technique, whatever, and see if you have the right answers based on that. Okay, so first one, question 1, just some simple algebra, rearrange equations kind of things. Let's start so again, I'm not going to do all of them, but let's say we'll use C as an example here, and let's just talk about how we can or how we should solve a question like this. So HT1 minus P naught over PF equals HA. Okay, so what is HT? What's this P naught? What's PF? What on earth are all of these things? Doesn't matter. They're just random letters. I could replace these with like triangle and minus square over star. Like it doesn't, they're just random symbols. We don't care what they are at all. The easiest way to think about these questions, this is just some like random physics formula I found on a physics website. I don't even know what this is. Doesn't matter. So the easy way to think about these questions, if it's hard for you to work on it like this, then just change the variables into numbers. Let's say 2 times 1 minus 3 over PF, that's our targets, equals, let's say, 5. Okay, so if we look at it like this, and I tell you, tell me what PF equals, solve for PF, then it's probably a little easier to think about, right? So let's try this. Looking at this version on the right here, if I want to solve for PF, what's the first thing I should do?
Divide both sides by 2.
Okay, so the 2 here on the outside, that's the furthest away thing from PF. It's on the outside of the brackets. So we take care of that first. So divide both sides by 2, 1 minus 3 over PF equals, and I'm not gonna evaluate this. I'll just leave it as 5 over 2. That way it'd be very easy to just switch back to all these terms at the end. What's the next thing we could do?
Professor, can I ask a question?
Sure.
Couldn't we just do expanding on the first step?
You could. I don't think that's necessary. It seems easier to just, like if we do this, then we have our HT. Let's write this over here. 1 minus P naught over PF equals HA over HT. This seems simpler to me. Like we're not trying to consider what the goal is. Like if we're trying to isolate PF, then multiplying HT by both of these things isn't really necessary. It would still work and we could still get a solution. I think the solution would end up looking a little more complicated than necessary. So it's not wrong, but it's not the simplest thing that we could do. So there's no, some people had a lot of trouble on this question and ended up like getting squares and square roots and things and all kinds of stuff that is really unnecessary. Just a few simple steps would have been enough to solve it. So let's try to look at the simplest possible way of solving for PF. So let's look over here on the right again. What's the next thing that we could do?
Move the 1.
Okay, so there's 1. This is the next furthest thing away. Let's try to get rid of that 1. I'm gonna do it this way. We'll take the 3 over PF, move that over to the right side. So add that to both sides. At the same time, let's take the 5 over 2 and switch that over to the left side. So that will give us 1 minus 5 over 2 equals 3 over PF. Okay, what now?
Cross multiply the PF to the left side.
Okay, so
I mean, yeah, just multiply both sides by PF.
okay, so take PF here and we'll just multiply both sides by this. So PF 1 minus 5 over 2 equals 3. We could have also taken just both sides and just flip them, inverse them to get PF sort of on the top of the fraction, then divide by 3, but doesn't matter. Okay, so then we're here and one final step.
Three divided by 1 minus 5 over 2.
Yeah, so just the thing that now we are multiplying by PF, just divide by that. So 3 over 1 minus 5 over 2. And if we're here, I remember what the 3 is and what the 5 actually is and what the 2 actually is. I can just very easily take this and rewrite PF equals, what was the 3? It was P naught over 1 minus HA over HT. So this is a way of thinking about these questions. If it's just numbers, it's probably more intuitive and more natural to think about it. But the exact same skill, the exact same technique, you know, if we have an adding, then we subtract to eliminate it or whatever, is being used to get the result that we have on the left here. So that's the easy way, or I think the easiest way to think about these kinds of questions. But it's just really core algebra rules. Divide both sides by something, multiply both sides by something, subtract something from both sides. So that was question 1. Again, there were other ways of having it where you've isolated PF, but we don't want unnecessary complication. If there's a simpler way of expressing it, that's the better way. All right, moving on to our next question. Equations of lines. This one also meant to be just a kind of a quick, easy, early question on the exam. We have 3 lines here, and we're just first looking for the equations of each of these lines. So we can just see them on the graph. So the first one, f of x, here's a point, here's a point. Okay, what's our delta y between those 2 points? It's 1. And what's our delta x between those 2 points? It's, sorry, let's write this over a little further. 1 over, it's 4. So there's our slope, it's 1/4. We could also have like put in the y2 minus y1 like that if we want, but it's possible to just directly read the slope from the graph, 1/4. What's the b value? Well, it's right there, the y-intercept, we see it, it's 5. So b value is 5, so therefore y equals 1/4 x plus 5. Oh, not b, 5. We can just see it from the graph, done. H, we can do the same thing. We could just see all the numbers we need directly off the graph. H, we can see the slope pretty easily, except we just need to do a little more work to figure out what the intercept is. So for G, we would have our equation y equals, that's a slope of 5x plus b, and then just substitute in one of the points for the y and the x, solve for b. So fairly straightforward question, just finding the equations. The second part of that is asking us to find points of intersection. So we can see 2 points of intersection here. The graph doesn't cleanly show us what they are, so we know approximately what they are. So this one on the right is going to be like 1.6, 1.7 around there, and then 5.3, 5.4, but we should do some algebra to find out exactly what it is. So 2 equations, 2 unknowns. That's a pretty simple system of equations to solve, substitution or elimination, and you can figure out the exact point of intersection of those 2 for D and E. F is a little different. What's the point of intersection of G of X and H of X?
Yeah, they do not intersect.
Okay, they don't intersect. So lots of ways we could see this. We could see the 2 slopes, see that the slopes are the same. So therefore they're parallel and they're not going to meet. Or we could do our algebra and try to solve for the points through substitution or elimination. And then we do whatever, we get some result like 3 equals 10. And then we say, wait, no, that does not equal 10. That's not true. There must be no point of intersection. So we could look at the graph and just use the slopes, or we could do the algebra, however you wanted to show that there was no point of intersection. Okay, so some early straightforward questions here. Q3, so break-even question. This, I don't know if I'd really call this a trick or like a challenge, but something slightly beyond what we've done in class. So break-even questions, how do we start them? What we need to build 2 different kinds of equations. What are those?
TC and TR.
Right, so we need our total revenue equation. We need a total cost equation, these 2 things. Okay, total revenue is what?
Quantity
P times Q.
multiplied by the selling price.
Right, the selling price. So P times Q. In this case, what is P?
7,000.
Right, it's right here. So average price per unit, 7,000. So TR, 7,000 Q. How do we figure out total cost?
Fixed cost plus variable cost.
Okay, what's our variable cost, our per unit cost?
3,000.
3,000, which we get right here. Average cost to make each of these units of bread, so 3,000 Q. Okay, and then fixed costs. What are the fixed costs for this problem?
16 million.
So one more time.
50 million. 16 million plus 50 million.
Okay, this one plus this one. So to know that, you have to read the question, and it says that these are costs, but what kind of costs are they? Are they variable costs or fixed cost? Well, it tells us 50 million first of all, if it's like 50 million as a variable cost, like for each loaf of bread, you have to pay 50, that's 50 million, that sounds wrong, like intuitively. But also it tells us here, 50 million won for the building and the storefront. For each unit of bread that we sell, do we build a brand new building? No, we build the building once and sell lots of units of bread from that same building. That's a one-time cost, not dependent on Q. The cost does not go up or down based on changes in Q, therefore fixed cost. And we see the other thing here, 16 million for bakery equipment, same idea. You don't buy a new oven for each piece of bread, you just keep reusing it. It's a one-time cost, so that's a fixed cost. So the fixed costs here are 66. I'm just gonna be lazy and not write the zeros. 66 million. We just have to add these two numbers together. So in class, we only saw questions where it's just, here are the fixed costs, but here we had two things, add them together. So I don't know if I'd really call that a challenge, but slightly different from what we've seen in class, or what we had seen in class. Okay, and then how do we find a break-even point based on this?
Profit equals to 0.
Okay, so our profits, which is
Total revenue minus total costs.
Right, TR minus TC, we set that equal to 0. So when 0 equals TR minus TC, in that particular case, then we will have, I think I have enough space down here. So we will get our 7,000 minus 3,000. Actually, I need to write this out to explain something. So minus bracket 3,000 plus 66 million. A surprisingly common mistake that I saw is people forgot about these brackets here. So when they wrote plus 66 million on their next line, they wrote, okay, simplify this. That means it's 7,000 Q plus 66 million. But it's not plus 66 million, it's minus. That's a fixed cost because they forgot about the brackets, forgot to apply the negative to both of the terms inside the bracket. So 7,000 Q, sorry, not 7,000. I forgot to do that subtraction. 4,000, that's better. 4,000 Q minus 66 million. That is equal to 0. And then we use that to solve for Q. And therefore Q is whatever number. I think it was 16,500 for that question. So that's how we solve this. So that was A. B had a slightly different scenario. Almost everything was the same, but just one part changed for B. What was that one part?
The variable cost.
Variable cost. So if the variable cost, actually, let's just rewrite it here. Instead of 3,000, it's 4,000. Also, it's a word problem. We have to read the problem carefully. It increases to 4,000, not increasing by 4,000. So the new variable cost is 4,000, not 7,000. So 4,000 Q and then dot, 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 that turns into a 4, that becomes a 3, and then our solution, the Q value was something different. I think it was 22,000 in this case. Okay, so that's B. So just basically do the question again, but change one number. And then each of these, there was just a little bit extra on these. Okay, so find our Q value, and then with that Q value, find out what's the total cost at the break-even points. And for question B as well, find out what the total revenue is at the break-even point. We just take those numbers and we solve them, sub them back in. So 7,000 times this thing would give us the total revenue. Or it's a break-even point. So at the break-even point, total revenue equals total cost. So we could have substituted our Q value back into either one of these equations and still gotten the exact same number because it's the break-even point. So that's how we do 3. Scenario, or part C here was asking us, okay, instead of break even, instead of 0 profit, what if we want to actually have some profit of this much, of 30 million? So we would just do the same problem again. We'd have our profits equals TR minus TC, except now we want 30 million equals when our total take our total revenue, subtract the total cost, and the result should be 30 million. What Q value will give us this? Use the same things that we had on the other side, the 4,000 Q minus 66, but then with this 30 mil here as well. And then what's our Q value to get that exact profit? Okay, so that was 3. Break-even questions are usually in a practical sense, so we should be able to kind of read a word problem and pull out the kind of key information that will help us solve it. Anyone have questions about question 3? Okay, let's go on. Question 4, this is a matrix elimination question. So there was nothing weird or special about this question, just a very straightforward kind of standard version of this kind of question, like we had done in class 1, 1, 2, 9. Convert it to a matrix, do our row operations, try to get down to that kind of triangle form, and then just to the main diagonal, and then it's solved. This question, we could have started by taking row 1 and row 3 and swapping them to put a 1 in the first position. We also might have been clever and noticed that we have the same kind of scale here. So if I use row 1 or 2 to eliminate the other, then I would get 2 zeros right away, and I could instantly solve for the Z value. Few different ways it could have been done. There were lots of little kind of opportunities for shortcuts like that, but not meant to be a special or difficult question here. Just matrix elimination, same standard approach we normally did. Okay, the linear programming ones, these are a little harder. So the setup for these can be trickier. So let's talk about this a little bit here. Linear programming, first step is always identifying variables. So for this problem, bakery, 3 different kinds of bread that they're making. They have this operating cost. What are the variables that work for this problem?
Probably O and N.
Okay, representing what?
Number of hours that each bakery operates per day.
Okay. I don't like using a variable of O because it looks like a 0. So we could just use X or Y, or maybe I use D as an older bakery or something, and new. But yeah, so those are the variables that make sense. So D here would be number of hours of operation for the older bakery, and then N as the same thing, but for the newer bakery. Okay, how do we figure that out? How do we know that? The question is giving us a number of hints for this. So first of all, or the main thing is in part B, this is our objective, our goal. So minimize cost. That's our end objective, minimize cost. Well, where are costs coming from? We can look at our table here and say, well, the costs are coming from, it's not like the ingredients for the bread or whatever. We're not thinking about that. The main costs we care about are operating the bakery. So each hour it's open and baking stuff, then money has to go into it to pay the people and whatever. So number of hours it's operating determines the cost. Okay. And the question part B is also telling us, find the number of hours that each bakery should operate. So that also is telling us, okay, these are what the variables should be. This is the thing that we get to decide freely. The rest is just sort of automatically determined for us or is dependent on these things. But number of hours to operate each bakery is the flexible thing. So those are what the variables will be. The constraints then are how much of each of these things, types of bread that we have to make. 1, 2, 3. Let's build one constraint inequality just as an example. I won't do all of them, but let's take the baguettes. How can we use our two variables to express our baguette constraint with an inequality?
10d plus 80n
10d
greater
plus
than
80n.
greater than or equals to 400.
Okay. Now, a thing that lots of people have trouble with is the sign on the inequality, the direction. Why are you saying greater than and not less than?
Because we need to minimize. Our goal is minimization.
Okay. Yes. There's a little more logic we can add to it.
It's because 400 is the minimum daily output required. So we have to make 400 or more than 400.
Okay, so the problem is telling us minimum daily amount. If we make exactly 400, yes, that's okay. If we make over 400, well, we've still made the minimum. That's fine. We just have some extra. If we make under 400, well, we haven't hit the minimum, so that's not okay. So the number must be 400 or more than that, so that's greater than. Also, what Timothy said with the minimization problem, usually a minimization problem will look like this and one. So in this case, we had 3 different constraints and we would end up shading above all of them. So greater than or equal to that will be above the line rather than below the line. So usually, yes, if you see a minimization problem, then we would sort of be shading above and they'll probably be greater than or equal. But there can be problems where some are greater than and some are less than. So we see minimize, okay, probably greater than, but let's look carefully at what the actual constraints are and make sure that the logic holds for each particular one and make sure that we have the signs correct. So 2 different things we can look at to help us figure out what the sign will be. All right, exact same thing for the other 2. And then we have our objective function, which should be here. So 400d plus 700n. And then we put that on our graph somewhere. And it turned out that this point, if we had d on this axis and n on the vertical axis, this point here was the one that ended up being the best. I think it was 8, 4.
8, 4.
If I remember
8, 4.
correctly. Yeah.
Yeah.
Okay. So that was the points. And if we had our graph, it would look like this. The numbers were designed so that even if you didn't have a didn't have a ruler and your scale was a little bit off, like you could have made a fair number of kind of not mistakes, but not having like a super precise graph, and still found that point to be the best one. There would have had to have been a lot of mistakes with the graph to not get that particular point as the target one. Okay, so that's the linear programming. And then the slack constraints. I know slack, that was a harder thing. Very few students were able to, maybe it was just an issue of time, but this point of intersection, it's for 2 of the lines. So then the one that isn't touching, that's the one that's slack. And we could calculate exactly how much slack there was. That was part C. Okay. Let's go on. 3 more here. Matrices, matrix arithmetic, matrix operations this time. I have taken out the numbers because we don't even need them to be able to talk about these questions. Okay, first one, a plus b minus a. What's the solution?
It's just matrix B.
All right, it's just B. We talked about in class how with matrix, not matrix multiplication, but yes, with matrix addition and subtraction, if we change the order, we still get the same result. So a plus b minus a is equal to a minus a plus b. A minus a would just be a null matrix plus b, therefore b. There were 1 or 2 people, or not 1 or 2, there were a handful of people who were kind of clever and noticed this and then didn't write out the actual numbers. They just realized, oh, it's just b. We can just write that. But most people wrote out the numbers. That's fine. You still got the results. It's b. So, which was 10, -9, or whatever the numbers were, the result is B. So A and E, most people were okay with. When I saw mistakes with A, it was because people like wrote minus A, but when they did the actual operation, they were adding here, or they tried to add C or something. They didn't use A for the third value there. Okay, so let's talk about B. There were a number of mistakes with part B here. B plus C. Undefined. Okay, tell me why.
Because the dimensions are different. When we subtract and add matrices, the dimensions should be the exact same.
Okay, so should have the same dimensions. A lot of people said for part B, well, we can't do it because the number of columns of B and the number of rows of C don't match. It's true that they don't match, but that's not why the matrix addition doesn't work. That's the condition for matrix multiplication. As I highlighted in class, matrix multiplication is weird and has weird rules that are very different from other ones, very different from other operations. So just to make that point a little more strongly here. Let's say we have another matrix that's this, and it's matrix D. It's the same size as C. If we took that logic and we said, okay, well, number of columns of C, number of rows of D, they don't match, but addition is still possible because they have the same dimensions, C and D. So the reason that it doesn't work is because B has 2 rows and C has 3 rows. That's the mismatch. That's why the operation is not possible. All right. C times B, the next question. C times B. Is this possible?
Yes.
Yes. Okay. So C is a 3×2 matrix. B is a 2×2 matrix. Inside numbers match, 2 and 2. So Yes, it works. Two common mistakes that I saw. One was people writing matrix C. They wrote the size as a 2 by 3 matrix. They wrote the columns first and then the rows second. And then they said, well, B is a 2 by 2. Inside numbers don't match, so it's not possible. As I stressed this in class as well, for matrices, you need to talk about the sizes as rows first, then columns second. You can't just, change it freely, because if you do, you make exactly this mistake with matrix multiplication. So have to talk about the rows first and then the columns second. Other common mistake was people said, well, let's C times B, and then they wrote it like this. Well, B is a 2 by 2, C is a 3 by 2, and the inside numbers don't match. Matrix multiplication, we can't change the order, or if we change the order, we change the question completely. We have to evaluate it as stated in the order given. So can we do C times B in that order? All right, last one I'll talk about here, D. Some people had trouble reading D. So can someone just read out loud question D for us? What exactly does it say?
7i multiplied by C.
7i. I is our special identity matrix. A lot of people read it as 71. It's not a 71, it's a 7i identity matrix. Okay, so if we have I times C is going to happen. C is a 3 by 2 matrix. What size must I be, matrix I, in order to be multiplied by C?
2 times 2.
So it's a 3 by 3 matrix. I must be a 3 by 3 because that's the only way to make the inside numbers match here. So I must be a 3 by 3 matrix. So 7 times I would give us 7, 7, 7. And then all zeros, identity matrix, just times a scalar, 7 would give us this. And then we multiply that by matrix C, and we work out, okay, here are the results. Some people also noticed that if we change the order a little bit, I times C is just C. Multiplying something by the identity matrix doesn't change it. So this is actually the same as just doing 7C. So just multiply everything in C by 7, and then we'll get our result. So a few different ways of thinking about it that would give us this result. But identity matrix, choose the size. There's only one size that will work. So use exactly that size. Okay, so those were the matrix arithmetic questions. Does anyone have questions about this? Okay. All right. Last two things here. I won't spend as much time on these ones. So systems of inequalities. We had a preview question that was like this, and linear programming was all built on these ideas. It was sort of a harder version of this kind of thing. So A here, well, we can find the equations of these 3 different lines and then just turn them into inequalities. So for the line on the bottom here, it should be y is greater than something because we're shading above that line. For the one above, it's y is less than because we're shading below that line. And the one on the right, it's a special case. A lot of people tried to write it as a y equals something, but perfectly vertical lines, equations are just x. So x equals something, or in this case, x is less than 1 because it's a perfectly vertical line going through the point 1 on the x-axis. So just those, figure out what those three are. And again, we can just read the values off the graph for the most part, maybe some small calculations to figure out the points of intersection for B, the B values for each of these, and then just turn them into a system. And there's our solution. Question B, part B, that was probably the hardest question on the exam. It is not solvable. So there's no, given the way that we have been talking about systems of inequalities, there's no way to write them that would create shape B. That's what I was hoping people would recognize. This inner shape. Let's try that again. This inner shape and then taking out these little kind of wings sticking out on the side here. Those could not be included. That's the best that we could do. Or one person said, well, we could have this inequality, but kind of limit it to this particular range, and then we could describe it. So we could say it's impossible because can't include those little outside parts, or here's kind of a special version of it. Those are two different ways that could have been solved, but hardest question. Last one, proof. We have this property. And like, is the left side equal to the right side? Let's say just for easy case here, just for 2 by 2 matrices. So the way to address this one, let's just make some matrix G and call it whatever, give it whatever values. So let's say G1, G2, G3, G4. And then we do the same thing for H. Make up another one, H1, H2, H3, H4. And then just calculate each of these results. So G transpose, then H transpose, then multiply the two of them together. What do we get? We get this thing, this kind of big result. And then let's do the other one. Let's do H times G, then take the transpose of that, and then compare the two. Are they the same or are they different? And it turns out that they are the same. And yes, this is actually like a rule about matrix operations. That's true. Some people try to do this as like treating the t's like a like an exponent. That doesn't work. We can do this just with the rules of transpose and rules of matrix multiplication, just with some kind of arbitrary variables in the positions. Also a pretty difficult question on the exam. So 7 and 8 were meant to be more challenging for sure. Okay, so that's, again, I haven't gone through full solutions here, but these are the strategies. Hopefully, if you had trouble with some of these questions, hearing my explanation now, you could go back and give them another shot and know how to address them. Does anyone want to ask other questions about any of these exam questions here? Okay. All right, let's go on then. So the second half of the course is about nonlinear algebra, as I mentioned. So sequences in series, we'll do arithmetic for a little bit and then geometric sequences in series. So we're going to need exponents for that. We will apply that to interest and we need exponents for that. We'll talk about slopes and sort of limits and graphing nonlinear equations, which we'll need exponents for that. And then we'll apply that stuff to calculus and we'll need exponents for that. So good to do some kind of review right now about some exponent rules. So if you remember from way back in like the very first week, I talked about that website called algebrarules.com and had some sort of just fractions and multiplying and dividing and adding and fractions and such. The second set of rules on that site are all about exponents. And it's these rules you see right here. So these are all the exponent rules that we can use and keep in mind to help us work with exponents. So there are a lot here. We'll do some review questions first, and then I'll come back to this, come back to this list, and we'll talk about sort of a subset of these, the most important ones of these to focus on. But let's get started with these. So we'll just quickly review the vocabulary that we need to talk about these. This also we did at the beginning of the semester, but we haven't been talking about exponents so much. So let's just do a quick review. If we have something like this, we have the base, and then the little number up top is the exponent, and then the two together, B here, is the power. It's the result of the two. We also, if we're having a root like this, we can have these words radicand and index. Nobody uses these words, or like very rarely. I am certainly not going to use these words in class, but they're there if you want to know them. So if we read an exponent, normally it's like this: a to the exponent n. You'll hear a lot of math teachers, instead of exponent, they'll say power. I think that is technically inaccurate because, again, power is this thing, but whatever, lots of people say that. And in class, just because it will take too long, I might just sort of say a exponent n like this, just to be shorter and a little faster. So two special cases. So in something, generally a to the exponent n, but special cases, we have, if it's a 2, we say squared. If it's a 3, we say cubed. For roots, similar idea. This is a square root of something. This is a cube root of something, not cube square root, just cube root of something. More generally, this would be the nth root of whatever number, 5th root of b, 12th root of b, like that. So that's the vocabulary that we will need: squared, cube, square root, cube root, and then nth roots, or a to the exponent n, like that. Okay, let's get into these. So each of these, I have some simple review questions up here, and then the rules that you can use to help you solve them will be down in the bottom corner. The easy ones we'll go through quickly. The harder, slightly harder ones will take a little more time on. So first, 9 to the exponent 0. What does that equal?
1.
1.
It is 1. What if we don't know what the number is and it's just some variable
Still
n?
1.
It's still 1. We don't care what the number is. It's always 1. Easy rule. Next one. Negative exponents. So if we have a negative exponent, that means it's 1 over whatever that thing is. And if that thing is a fraction, then 1 over that thing, that basically just means we flip over the fraction. So take 20 seconds, 30 seconds right now, try to solve these questions, and then we'll talk about the answers. All right, first one, x to the exponent -5. How can we simplify this?
1 over x to the exponent of 5.
Good. 1 over x to the exponent 5. Not always, but a lot of textbooks or whatever will say if you have a negative exponent, you should switch it over to get rid of the negative sign in the exponent and make it sort of a 1 over or something like this. It's not like necessary, but sort of it's a good habit to get into. Sort of, it's often preferred. Okay, next one, 10 to the exponent -3.
1 over 1000.
1 over, okay, so I'm gonna just do 2 steps here. 1 over 10 cubed, and then obviously 10 cubed is 1 over, turns into 1 over 1000 here. Okay, next one, 1 over y to the exponent -4.
Y to the exponent of 4.
Okay, so y to the exponent 4, I'll add an extra step here. 1 over y to the exponent 4. If it's 1 over something, we can just think about our dividing fractions. So you invert and multiply. Turns out y to the exponent 4. Last one. We'll do multiple steps. Give me just the first step here first.
1 over 5 over 7 squared.
Okay, one more step from that. Using the rule that we have down here.
Oh,
To invert
flip
the
that.
fraction.
Okay, so just flip over the fraction, get rid of the negative on the exponent. So 7 over 5
Squared.
and that whole thing squared. And then as the next rule we'll see in a little bit, we can take our exponent on the outside, bring it inside our brackets here and say, okay, well, this is 7 squared over 5 squared, and we can simplify that to 49 over 25 like this. But the main thing here is this. The reason the fraction flips over is what Vincent was saying. It's 1 over 5 over 7, then do the dividing by fraction, etc. And it turns out that the fraction just flips over. Okay, so negative exponents, that's what happens. Next one. If we have the same base, 2 bases, so a on both of these that are being multiplied together, but we have different exponents, then we can add those exponents together. That's the rule. So take a few seconds, try out these questions. Okay, first one, y to the exponent 5 times y exponent 6.
Y to the exponent 11.
Okay, y exponent 11. I'll write out a few more steps here. Y exponent 11, y exponent 5 plus 6. If we just think for a moment about why this is, y to the exponent 5 is y times y times y times y times y 5 times, and then also all of that multiplied by y times itself dot 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 6 times, and then we just add them together. How many y's do we have being multiplied together? We have 11 of them, so 5 plus 6, 11, so just 11. So that's the logic behind that rule. Next one here, 2 to the exponent x times 2 to the exponent 3x.
2 to the exponent 4x. And that
Or-
equals to
over x, so x plus 3x. Can we simplify this further?
Yes, of course. That will be 16 to the exponent x.
16 to the exponent x, you're saying. Okay. Let's we'll leave this one like this. We have some other rules later where we'll kind of bring in some other stuff, but let's for this point, let's just leave this version like this. And our third one here, how can we simplify?
Is it 6a to the exponent of 8?
Okay, 6a exponent 8. Because multiplication, we can reverse the order, not the regular multiplication, not matrix multiplication. We can reverse the order. So this is just 2 times 3 times a exponent 7 times a. Then we just combine and simplify, and we get 6a to the exponent 8. Okay. I should have given people a little more time to write on the previous one, but I'm going to go on. In 3, 2, I don't know if you want to take a screenshot or something. Okay. Next one, exact same idea, except we have fractions and subtracting exponents rather than adding exponents. So take a few seconds, try out these questions. Okay, first one, x to the exponent 9 over x to the exponent 7.
X squared.
X squared. So it's x to the exponent 9 minus 7. 9 minus 7 is 2, so x squared. Next one.
3 to the exponent of 8.
3 to the exponent 8. And that one, you know, we could simplify that. That's an actual number. I think it's 2,401, if I remember these correctly. But anyways, that's a number we could easily figure out. But we'll just leave that for now. And our last one here.
B to the exponent of -4.
B to the exponent -4. And if we kind of hold to our little formality rules about not liking negative exponents.
1 over
1
b.
over b to the exponent 4.
Right, 1 over b to the exponent 4, like this. Okay, so we'll go on. We have 2 more of these pages, I think. Yes, the last one's not very hard. These will be kind of the hardest ones that we'll have here. So 3 different rules. First, if we have different bases being multiplied, but the exponent is the same, then we can just factor out that exponent. Multiply your bases, do the exponent afterward, it'll be the same thing. Basically the exact same rule, except for dividing with fractions. So we can just factor out the same exponent if we have it, if we are dividing like this. Third one, a little different. If we have an exponent to another exponent, then that means that we are actually just multiplying, not adding, but multiplying the 2 exponents together. Okay, so use those rules and take a shot at these questions here. I'll give you a bit more time to work on these ones. Okay, let's try these questions here. So first one, A, how can we, I want to do this in 2 steps. Tell me the first step we could do. Let's just bring our exponent inside the brackets.
-3 cubed
Okay, so -3 cubed and
multiplied by m cubed multiplied by n cubed.
m cubed and cubed. So we just take our exponent from the outside, bring it in, apply it to each of the parts inside, and then the -3 cubed, that's just -27 m cubed and cubed. Okay, next question.
Okay, so -3 goes to both k and j. So we have
Yes, but there's an easier way of thinking about it.
Just flip it, right?
Okay, so let's do the negative exponent first, then we'll do the 3. We can think of this, if this is -3, that's the same as -1 and also 3. So let's do the negative,
yeah.
flip over the fraction, j over k, all of that cubed, then what?
J cubed over k cubed.
Okay, so j cubed over k cubed. If we did the -3, brought it inside for each of them, it'd be 1 over k over 1 over j, and then dividing fraction rules, we would still end up with j over k. It's just a little more complicated to think about. Okay, the last one has a little more going on here. So we'll do it step by step. What's the first step to simplify question D?
4 squared multiplied by p exponent -6.
Okay, so we're gonna I'm gonna give us one more step even here. So I'll say we have the top of the fraction, 4p exponent -3 squared over, and then the whole thing on the bottom, q squared squared. So we just bring our exponent in from kind of the larger brackets here and apply it to the top and the bottom of the fraction. And then what's the next step we would have?
(16) px to the exponent of -6 over q exponent 4.
Okay. You're also jumping ahead. You're totally right. I just want to make sure everyone can see what we're doing here. So next, I'll just bring the exponent inside. So here, this would be 4 squared times p, the exponent -3, and all of that would be then squared. So bringing our exponent from the outside inside each of the parts there, and then all of that over on the bottom, bring in our exponent 2 times 2 here. Okay, and now we'll do the step that Vincent just mentioned. So that's 16 on the top, 4 squared is 16 times p to the exponent -6, -3 times 2, that's -6, over on the bottom, q to the exponent 4. And then I want to do one more to, again, get rid of the negative exponent we have on the top.
1 over p to the exponent 6, and p to the exponent 6 goes to the q to the exponent 4.
Okay, so that would end up going to the bottom of the fraction here.
Yes, and it will q to the exponent 4 multiplied by p to the exponent 6.
Okay. So the p to the exponent -6 would turn into 1 over p to the exponent 6. And then when we bring that back in, then we combine it like this. And then just basically, it's a negative exponent. It's going to send it to the bottom of the fraction. And this would be our sort of ideal, most simple version of this, simplified version of this. Okay, so 3 different rules here. These ones may be a little more complicated, or they can be combined in different complicated ways here. Our last one will be about roots. So exponents and roots are the exact same thing. We just write them differently. So let's take these 2 things, do some rewriting, figure out the actual values here. So take a few moments, go ahead and try to simplify these. Take another moment to solve these. Someone at my door, might be something important. I'll be back in a second. I have an elderly neighbor who, whenever she has problems with her cell phone, not knowing how to use an app or something, she comes and asks me to show her what to do. Okay, so first one here. There are 2 things that we could do. So let's see what each of them is and then talk about which one would be more convenient. So what's one way we could rewrite the first one?
Cube root of 125 squared.
Where's the squared going? Inside the cube root or outside?
Outside.
Okay, so this is 1 cube root of 125, and then all of that squared. I'll add brackets here just for clarity. What's the other way we could write this?
Um, 125 to the exponent of 1 over 3 squared.
Okay, we'll still use the root. I'm thinking the other way we could write this is cube root of 125 squared. So just basically, do we want to do the cube root first or do the square first? They're both exponents, so the order doesn't matter here. We just do whatever's easier. So if we think this one, 125 squared, do we know what that is in our head? That's probably not a super easy number to just kind of like say or jump to right away. But what about the other side? Cube root of 125. Can you tell me what that is?
5.
That's 5. So that one, maybe we know that might be a little quicker to jump to. So 5 squared and then that's 25. The other one, again, it would still work. We'd still get the same answer, but it's just a little harder to think about. So if you have these two options, just do what's easier. That's it. Okay.
But they both are all right.
Yeah, they're both fine. They're mathematically equal. It's just whichever way makes it easier for you to think about it.
Okay, thank you.
All right. And for the next one.
1/4.
Okay. Well, a few steps here.
Equals 1/32 to the exponent 2/5.
Okay, so 1/32, negative exponents, so 2/5. Okay, and then we have kind of the same thing. We could do the 5th root first and then the squared second, or we could do the squared first and the 5th root second. Which one sounds easier?
5th root first.
5th
and
root
then
sounds
square.
easier first. So 5th root of 32, and then that whole thing squared. 5th root of 32, we probably know that's just 2 squared, so 1/4. So again, whichever way makes it easier for you to think about or to solve. Okay, those are the exponents rules. So we'll go back to this slide. These are all of them. You don't really need to learn or memorize all of these, I don't think. Instead, you could just learn or memorize these 5. So that first, roots and exponents, roots and fractional exponents are the same thing. Second, a negative exponent means you just flip over, it's 1 over that thing. If you have the same base, excuse me, being multiplied together, you can just add the exponents. And if you have an exponent to an exponent, which still means the same base, then you can multiply the exponents. And then the last one, if you have same exponents, but different bases, you can factor out the exponent. So if you can remember these 5, the rest of these other ones just kind of follow automatically, just from the combining these rules, or just kind of from kind of logic or common sense from these. So if exponents are kind of a harder thing for you, or you've forgotten some stuff, focus on these 5, and that should get you through any exponents situations that you encounter. Okay, that's the exponent stuff. Hopefully, working with exponents, this is kind of coming back to you if you had forgotten some of that stuff. I have a whole bunch of review questions recommended here in the exponents, chapter 5.2 in our textbook. All these questions here are a good review on that. And then roots, I don't know why, but our question has them sort of, our textbook has them separately, but they're in here, chapter 8.2, 8.3. And then there are a whole bunch of review questions here that you can do that will be good for that. So you don't need to do all the review questions, but do the ones that are like harder for you, the ones that are about rules that you sort of forgot or whatever, and then figure those out. All right, for the next 2 classes or so, we'll be talking about arithmetic and geometric sequences, and then we'll afterward be applying that to interest examples. And then we'll move on to other stuff after that. Exam, again, probably grades and ranks reported to you by the end of today. That's the goal. We're pretty close to that, so that should be possible. And then if you have questions about the exam stuff, then schedule an appointment in office hours with me, and then we'll talk about that stuff. All right, we'll finish up here. So thank you for listening, everyone, and I will see you in Thursday.